So this is sigma y there. Same distance there, sigma y. And then same distance sigma y. Same distance sigma y. Okay, yeah? So the first step in Saint Bernard, you have to find this value. What is that? Sigma y over 1 plus mu. What is the value there? The other one is sigma y 1 minus mu. So the mu is Poisson ratio. Let's say the Poisson ratio is 0.3. So what do we have here? This is 200 divided by 1.3. What is the value there? The other one is 200 divided by 0.7. 1 minus 0.3. Let's say the Poisson ratio is 0.3. What is the value there, please? This one?
153.85.
153. This one?
285.71.
285. Are you sure? 285?
Yeah, yes.
Okay. And then what do we do? For this Saint Bernard method, draw a 45 degrees. That one 45 degree line there. Here, you draw a 45 degree straight there. 45, 45. Okay, draw 45 degree there, straight there. Line. This is the next step. And then you know that value is 200 there. Yeah, you know that value is 200 there. You know that value is 200 there. So this value 285 here, 100, 200, 300 there. 285 somewhere there. This is 250, 285 somewhere there. So what do we go there? Dot. Mark a point there. This is 285. Mark a point until you meet that line. Are you with me?
Yes.
And then you mark that 153 here. Where is 153 here? 200 there. There must be 100 there. 150 there, 153 somewhere there. Okay? This is 153. Are you with me? Until you meet the second diagonal there. And then you draw a straight line. Surprisingly, this line to here will meet exactly at 200. Because this one, the slope here. Are you with me?
Yes.
When you know this one meet 200 there, you do the same line there. This one meet this line here, meet till here. Meet 200 there. This is always 153 there. And then here, we meet this line again. We always meet 285 there. This is 285 there. Yeah? And then this line, through that line again, 153 again. Are you with me, guys?
Yes.
Very simple method. So this is what? These are the border of the failure limit. This is the border of the failure limit for Saint Bernard. So this theory is suitable for brittle material, Rankine and Saint Bernard. Yeah, not very suitable for ductile material. Okay, clear, guys?
Clear.
And then you mark the point. Let's say the sigma 1 is 150. The second one is minus 50, sigma principal. So 100, 150 somewhere there, minus 100, minus 50 there. So that is the line there. And then you draw a line from there to there. There's a happening, there's a limit. It's still positive. Happening and limit there. So it is still positive, the line. Okay? OL and OH. So safety factor is OL plus OH. Look from the graph here, it's still positive because it's still inside. So you can imagine the theory. Now the value must be positive. Let's say this value here. Sigma 1 minus mu sigma 2 is equal to sigma y over n. See that? Mu there. Sigma 1 minus sigma 2 is Tresca. 150 minus 50. This is 200. So this is another 0.3 there. So 150 minus 0.3 times 50 minus 50. So this is only 15. So this is only 165. So 165 is less than sigma, less than 200. Are you with me, guys?
Yes.
You can see the line there. If you use a Tresca, exactly H here, exactly on the line. But it's still outside a little bit. And this is Saint Bernard. 41 of you are here. What about the others? I'm afraid. What's wrong? Okay. Okay, never mind. Okay. This is Saint Bernard. Okay. What are the others that we have done? The Higgs, right? Higgs is also a curvature like the von Mises. Yeah? Are you finished with this, right? Yeah, the Higgs one. This is sigma 2, this is sigma 1. Again, this is 100, 200 there. This is sigma y. Sigma y. Sigma y. This is 200 border for the Higgs. So the Higgs part, how do we do the Higgs? Yeah? We have a guide. We draw the guide for Rankine first. Yeah, we draw the guide for Rankine. Yeah? And then we draw the guide for Tresca. Remember the Tresca is going outside here, going outside, okay? So the Rankine part, the Higgs, this is Higgs energy theory. The von Mises is a shear energy theory. So this energy theory here is not outside here. We start that quarter here, quadrant here, but it's not outside. Just inside of that line, but curve. You draw a. Are you with me?
Yes.
Same thing here. You draw inside the most curve that you can find. Just rugby ball, but inside, not outside. So the rugby ball more circular. It's not circular, but more circular than the rugby. Okay? Only after this one is outside. You continuously put line there. Continuously put line there. You see that?
Yes, can see.
Inside here and outside from, not outside from the square one, outside from the Tresca one. So of course, this is further outside more than the Tresca. Tresca will be more inside, right? Because this is a more circular one. So this is the Higgs limit for the Higgs. Are you with me, everybody?
Yes.
Easy, right? And then what is, let's say sigma 1 is equal to 150, sigma 2 is equal to minus 50. So 100 there, 150 there, 100 there, minus 50 there, somewhere there. So this is O. This is happening there. Draw line. So this is the limit. Yeah. So make sure when you do this, you compare. You compare your graph here. The bigger the graph, the more accurate of your calculation. Yeah. And you always compare with the theoretical. So for the graphical is what? Safety factor is equal to OL plus OH. Whatever it is here. Measure here, let's say here is 143 mm. And divide by 130 mm. Something like that. You got a 1 point something, 1.2, whatever it is. 1.21, whatever it is. And then you do the compare with the theoretical. What's that? Height here. Sigma 1 square plus sigma 2 square plus sigma 3 square. You don't have sigma 3 now. Minus sigma 1, sigma 2. Yeah? It's equal to sigma y over n. And square root that. So what do we have here?
No, doctor, we don't have the 2 mu, man.
Oh, sorry, yes, 2 mu. Minus 2 mu. For the no mu is the von Mises, right? So this 2 mu there. So this is 150 square plus minus 50 square minus 2 times 0.3 and times 150 times minus 50. Then square root there. Then you compare with 200 divided by n. And then you get your n there. Yeah, you always compare that value there. And then you calculate somewhere there 1.22 whatever. Very, very, very close actually. If you do the graph properly. Okay, clear guys?
Clear.
So this is the graphical method. Hope you are confident with that, okay? So what time is it now?
10:31.
10:31. Okay. Let us do some exercise reverse question. We have done on the first day the reverse question. Let us do that. This failure theory. Okay, we can do this exercise as a homework later on. Okay. What are the reverse question? But we do it by the Mohr circle. We have to do the Mohr circle. We have to find sigma 1, sigma 2, sigma 3. Okay. And we have to set a safety factor. Okay. Look at this. I used to use this diagram since 35 years ago, because you must understand the XYZ, the rotation and everything. So this is my P. This is 2 meter, 3 meter. The diameter is 1. The diameter is what is the diameter of this pen? Roughly, your eyes.
10 mm.
10 to 15, right? 10 to 15 mm. Can you imagine a 2 meter long there? 2 meter long, easily to bend, right?
Yes, very easy.
Even though this is a metal. You can imagine a metal there, still 2 meter long. Push a load there, easily to bend, because 10 mm is very small, right?
Yes.
So let us, I do because I want to make a bigger size than 50 mm. Yeah, 50 mm. So the question is, the yield is 200 megapascal. Yeah, 200 megapascal. Poisson ratio is 0.3. So the question is, what is P? Should I put there for it to be safe? by safety factor of 2. Find P max for it to be safe by safety factor of 2 using Tresca. I like to use Tresca because easy for calculation. But even though you show the graph there, Tresca and von Mises is not very far away, right? The border. Remember the border there? Tresca and von Mises is not very far away. So this is metal. What is the P there? So this is a reverse question. Are you with me?
Yes.
So what do we do there? Same procedure with the forward question. Where is the critical point there? I have to make a decision first because I want to draw the element where? Here, where? Here is the most dangerous one, right? Can you see that why this one is more dangerous one?
Because the 3 meter, then it's the limit until there.
See that? What is the difference between here and here? We have a torsion here and here, right?
Yes.
So by torsion, here and here is the same. Because torsion is 2P, right?
Yes.
By bending moment, here and here is 0 bending moment. Here is 3P bending moment. So we have a bending moment and torsion. 0 moment and torsion. So this is more critical. That's how you make a reason. Are you with me?
Yes.
What about this one? Here and here, 0 bending moment, 2P bending moment, but no torsion. So here is 2P bending moment. Here is 3P bending moment, plus torsion. Here, and here. Can you see that? The reason that. Are you with me?
Yes.
And then from here, where is the critical point? Because I have bending moment and torsion, right? So where is critical point? For bending moment, there, for this rod here, bending moment, yeah, zero stress there, maximum there, maximum tensile, maximum compression. For torsion, everywhere is the same tau. Can you see that, the reason?
Yes.
And then you decide, the top one is the most dangerous one. Why? The maximum tensile there and the torsion is everywhere the same. So we have a torsion or shear stress with maximum tensile. That's how you decide. You must see how it's getting the stress there. You must visualize and then you make a decision. I have to cut there. I draw the other side diagram. Yeah, draw the other side diagram. Same thing. P there, 2 and 3 there. I have to draw this diagram. Very important here. Cut from here and look from here. So P there times 2 is torsion there, rotating that way. So that must be a torsion there is equal to 2P. You see that? Everybody?
Yes.
P and 3 here, bending moment there, this axis, there's a moment there. Okay? Moment is equal to 3P. And then how does it affect on the element top here? This is the most important thing. Same procedure again. So A there. So A, you're looking from that side, A there. The leg of the A is that line here. This is the surface line. So this is how you draw your A there. And then 2P, remember this is 50 mm diameter. So this torsion here will create this surface there, will create a tau there. And this moment here will create a tensile there. So tau A and sigma A. So same thing there, going up going up there, going. Yeah, we got that one. So what is the value of sigma A? Sigma A is equal to M1 over I. Your M is in front of you there. Your M is 3P. Your Y is half of that 50. That's your Y there. Half 50, 25, 0.025 mm. This is in meter. And then your I, pi d to the power 4, 0.050 to the power 4 over 64. So the value in terms of P. What is the value in terms of P there?
Uh, 248 kilopascal.
248
0.2 P kilopascal.
kilo, 10 to the power of 3.
P.
248, 10 to the power of 3. Is that true? And then P there.
Let me calculate
And
again.
Anybody else confirm it?
Two four four.
10 to the power of 3.
P.
Same.
244, 10 to the power of 3P. Okay, no problem. Okay. Now we calculate the tau there. What is the tau there? Tau A is equal to in front of you there. TR over J. Okay, what's your T there? Can you read my writing there? Okay, what's your T there? Your T is 2P there. And then your R is that one. Your R is also 0.025. And then your J is pi D 0.05 to the power 4 over 32. So what is the value there?
$81.5 to times 10 to the power of 3 P.
81.
0.5.
81.5, 10 to the power of 3P. Okay, clear? Anybody confirm it?
Yes, same.
Okay. Okay. Can I wrap this one? Now I want to plot the Mohr circle for this. Remember the Mohr circle there? So this is 244, 10 to the power of 3P. And your tau there is 81. 81.5, 10 to the power of 3P. Yeah? Do the question and do a quick Mohr circle. Okay? Very Mohr circle there. Why I want to find Mohr circle? I want to find sigma 1, sigma 2, and then I want to do a 3D Mohr circle. I want to find sigma 1, sigma 2, sigma 3. I want to put into Tresca. Are you with me?
Yes.
Okay. So what do we have there? 244 and negative 85. 244. So you must be very precise in your head. It's 100 there. 100, 100, 100, 100, 100, 100, 100, 100, 100, 100, 100. Okay, 244, 200, 300, 250, 244 there. This 244, 85 negative. This 100, 50, 85 somewhere here. So this is 81. So this is your X surface. Read here 0 and 80 something. This is your Y. Draw a line. Same procedure. Are you with me?
Yes.
Yeah. Can you start again? What is the center? What is that length? What is that radius? What is that one? What is the theta? You can find that one, right? So
Yes.
this is 0, 244. Half of it must be 1 1 to 2, right? This must be 1 to 2. 1 to 2, right? This is 81.5. At 1 to 2 and 81.5. So what is that one? This might be 106. Okay. Push calculator quick. 1 to 2 and 81.5. What is the radius there?
146.7.
147.
7.
147. What is your sigma 1 there? 1 to 2 plus 147 is equal to what? 269. 10 to the power 3 P. Very simple. What is your sigma 2 there? 1 to 2 minus 147 is equal to
Negative 25.
negative 25. 10 to the power 3 P. Very quick there, very quick. And then I want to do a 3D Mohs circle. I draw that one, 3D Mohs circle. At the end of the day, where is my Mohs circle? There's another 0 there, that one, and then there's another one there. So this is my sigma 1, this must be sigma 2, this must be sigma 3. And then you write down, my sigma 1 is that one. 260, sorry, sigma 1, 269, 10 to the power 3 P. My sigma 2 is 0, my sigma 3 is minus 25 P. Very clear not?
Clear.
Clear. And then, after you finish here, you want to solve your Tresca. Tresca say what? Sigma 1 minus maximum minus minimum is equal to sigma y over n. My sigma 1 in this case is 269 10 to the power of 3p minus. Then your sigma 3 is minus 25 10 to the power of 3p minus plus. And then equal to your y is 210 to the power of 6. And then satisfactor, you decide, you put it 2 there. And then you solve that one. 69 plus 25, what do we have there?
294.
294, 10 to the power of 3p is equal to 200, 10 to the power of 6, and 2 there. So your p is equal to what?
340.14.
340.1.
4.
No power something.
No.
No. So this means what? What do you need of that?
Newton.
Newton. Okay? Because this is exactly the power, this is exactly the power to the power 6 there. And then the value is 340. So the value must be, load must be in Newton. Logic not? For 50 mm, about that size, 3 meter long, and put a load of 34 kilogram. Bending not? Are you with me?
Yes.
34 kilogram is 340 Newton, right?
Yeah, something like that.
But this is with certificate of 2, not failure. Remember that?
Yes.
Can you imagine that one? So you can feel. You can feel. I put the size 10 mm is not enough for that weight. 50 mm. Because the bending is so much. That's how you do the reverse work. It's all the same procedure, not?
Yes.
Same procedure. But I do the reverse work. Can I do the work is finding the, now I know this one, let's say I put this one is 300 Newton. But I don't know the size. What is the size there? For it to be safe, certificate of 2 or 2.5. Can I do that one? Yes, you can always do that one, and then the value is not, but the one must be diameter over 3 at the bottom there. Not P, but value over diameter to the power of 3. Why to the power of 3 there? Because the stress become diameter to the power of 3 there. Become, why become like that? Can you give the answer? Moment is equal to my over I. See that here, the moment is 3p, 3 times 300. And then your y is, you don't know the diameter. Your y is half a diameter, means diameter over 2. And then your I is pi d to the power 4 over 64. And then d and d here, that's why your unknown is numbers here, 248 over diameter of 3. Can you see the written there?
Yes.
The unknown is, you bring all together there, you can, and then you solve at the end there. You can solve your diameter. But the procedure is all the same. You draw the Mohr circle in terms of d to the power of 3. In terms of p. That's how you do a failure theory. Forward case, you know the load, you know the size, find the safety factor. Reverse case, I want this safety factor. I know the load, find the size. Or I know this, I want this safety factor. I know the size, find the maximum load I can put there. So this is the trick. So this is all the most difficult things in engineering. Because this is, it's not difficult actually. This subject is cover everything in engineering. Every engineer must understand this. If you don't understand this, it's no use you become an engineer. Understand is not by memorizing. You know from A to Z. Are you with me, guys?
Yes.
Okay. Thank you very much. We stop for today. I can continue tomorrow. Tomorrow we have class, right?
Yes.
Okay, I give some exercise. Okay, Assalamualaikum.